All right, let's continue on. We've learned how to test hypotheses about the beta parameters in a multiple regression model. But the process of making inferences about these parameters does not stop with hypothesis testing. In order to do a complete analysis, we also need to construct confidence interval estimates of these parameters. In addition to making inferences about the beta parameters in the model, we often need to make inferences about the mean of the response variable at particular settings of the explanatory variables. This includes both point estimation as well as confidence interval estimation. We'll be learning how to do all of these things in this lecture video. Now, to demonstrate the procedures that we'll be learning, we'll use SAS Analytics Pro. We'll use PROC IML to implement the estimation procedures that are presented in the textbook. We'll then look at how to easily obtain confidence intervals using PROC REG. So let's check it out. So we're going to look at confidence interval estimation in the context of multiple regression. To do that, let's think back to our first statistical methods class, where we first saw confidence interval estimation. How did we construct those confidence intervals? Well, we started off with a point estimator of the parameter that we were wanting to estimate. And then we went a distance to the left and a distance to the right from that point estimator, the distance being the margin of error. And that's how we got the lower and upper endpoints for that confidence interval. Well, we do the same thing here. We start off with a point estimator of beta sub j, if that's the parameter we're wanting to estimate. And then we go a distance to the left and to the right, that distance being the margin of error for that confidence interval. Now, the margin of error in all of these cases is the product of what is called an interval coefficient and the estimated standard error of the point estimator. And that's the same form we have here. The point estimator of beta sub j is beta sub j hat. The margin of error is the product of a t-value, and in particular, the upper alpha over 2 percentage point of a t-distribution with n minus p degrees of freedom. The n minus p, you'll recall, being the number of degrees of freedom associated with the mean squared error in the ANOVA table for the regression. That is the number of degrees of freedom that are associated with the estimator of the variance of the error term. So this margin of error is equal to the product of this interval coefficient, which in this case comes from the t-distribution, and the estimated standard error of beta hat sub j. Now, you'll recall from the notes that the estimated standard error of beta sub j is equal to the square root of c sub jj, and then we multiply that by sigma hat squared, again, our estimator of the variance of the error term, and that sigma hat squared is the mean squared error from that ANOVA table. So that is how we calculate the margin of error for a confidence interval for a particular slope coefficient. And to get the upper endpoint, we would just add that margin of error to the point estimator. So you see that this has the same fundamental form as the confidence intervals that you learned how to construct back even in your first methods class. And so example 3.8 deals with the delivery time data. And what we're going to do in that example, and we're going to look at and see how to do this in SAS in a few moments, but we will just take a look at what they're doing here. We're going to find a 95% confidence interval estimate for the parameter beta 1 in example 3.1. You'll recall that beta 1 is the slope coefficient on the variable x1, which is the number of cases to be delivered. Now, the point estimate of beta 1 is beta 1 hat, all right, which is 1.61591. And the x prime x inverse matrix, that is that matrix that they're calling C. And what we need to do is to get the entry in the, it's actually in the second diagonal position, but it's labeled C sub 1, 1 here. We multiply that by the estimated variance of the error term. Okay, so this would be the MSE from the ANOVA table, so 10.6239. All right, we multiply those together. That gives us the estimated variance of beta 1 hat. And then we have to take the square root of that. Okay, you see that happening right here to get the estimated standard error of beta 1 hat. We multiply that estimated standard error by the t value, which in this case is 2.074. Because we are constructing a 95% confidence interval, we have to get the upper 2.5 percentage point of the t distribution with n minus p degrees of freedom, which in this case is 22. All right, so that t value is 2.074. We multiply that by the estimated standard error of beta 1 hat. We subtract that from beta 1 hat to get the lower endpoint. We add it to the point estimate to get the upper endpoint. And so that would give us then a confidence interval that ranges from 1.26181 up to 1.97001. And so we can say that we are 95% confident that the true value of beta 1, the slope coefficient on x1, is somewhere between 1.26181 and 1.97001. Now, statistical software will typically give you the estimated standard error of these point estimates. And that's what they're talking about here. Minitab provides those standard errors. And SAS will give those standard errors as well. Now, the software may or may not allow you to request the confidence limits for the confidence intervals for those slope coefficients, but we'll see that SAS does allow that. All right, and then we also need to be able to estimate the mean of the response variable for a particular setting of the explanatory variables. We need to construct point estimates as well as constructing confidence interval estimates for that mean value. And again, the mean value of the response in a regression model, it depends on the values of the x variables, the explanatory variables that we're providing or that are at which we want to estimate the mean. All right, and so you can see here that again, the confidence interval has the same basic form. We start off with a point estimator for the quantity to be estimated. In this case, what we're wanting to estimate is the expected value of the response given particular values of the explanatory variables. The point estimate for that is denoted here by y hat sub 0. We'll see how to compute that in a second. All right, basically all we do is we just evaluate the fitted regression line or the regression model, the fitted regression model at the values provided in the x vector. So at the x values that we want to evaluate or estimate this mean, okay, we evaluate the model at those x values, and that gives us the point estimate for the response at that setting of the explanatory variables. So again, this confidence interval has the same fundamental form. We start off with a point estimator, and then we go a distance to the left and to the right from that point estimator, that distance being the margin of error. And the margin of error is equal to the product of an interval coefficient and the estimated standard error of the point estimator. Now, in this case, the estimated standard error of the point estimator, it's a little different because this is a different quantity that we're estimating, and the point estimator is different as well. All right, and so the estimated standard error of the point estimator for the expected value of y at a particular value of x is the square root of sigma hat squared, or MSE. And then we have this quadratic form. So it's x sub 0 prime times the inverse of x prime x, and then post multiplied by x sub 0. So that's a matrix way of writing that quadratic form. All right, that turns out to be a number. That's a scalar. We multiply that by the MSE, and then we take the square root of that. to get the estimated standard error of y hat sub 0. We multiply that by the appropriate t-value. And notice that the t-value here is the same as it was in the previous case. And that product then gives us the margin of error. We subtract that margin of error from y hat sub 0, add it to y hat sub 0 to get the lower and upper endpoints for that confidence interval. It has, by the way, a confidence level of 1 minus alpha times 100%. And so example 3.9 is going to demonstrate this. All right, and so let's take a look. So the soft drink bottler in example 3.1 would like to construct a 95% confidence interval on the mean delivery time for an outlet requiring x1 equal to 8 cases where the distance to be walked is x2 equal to 275 feet. And so the quantities in the x vector at which we want to estimate the expected value of y would contain 1 and then 8 and then 275. So remember that we need that 1 to multiply against the intercept. And then the value for x1 is 8. The value for x2 is 275. All right, to find the fitted value at that particular point, we can evaluate the fitted model as we typically would, or we can, if we want to represent this as a using matrix notation, it would be the inner product of the x sub 0 vector and the parameter estimates vector. So x0 prime times beta hat. And when we do that, we get the point estimate for the average delivery time when there are 8 cases to deliver and the delivery driver has to walk 275 feet to the location. And that average value is estimated to be 19.22 minutes. Now, to get the lower and upper endpoints of this confidence interval, we need to calculate the estimated standard error of this point estimator. And so to do that, again, we multiply the MSE, sigma hat squared, times this quadratic form. All right, so the MSE was 10.6239. And then we have x0 prime, so 1, this row vector containing values 1, 8, and 275, multiplied against the inverse of the x prime x matrix, and then that is post-multiplied by the x sub 0 vector. All right, so that's a matrix equation. It's you know, a little bit cumbersome to do. If you've got a calculator, you could do this. If we have computer software, you know, we could do it in PROC IML, which we'll see. All right, but when we do that, we get a value to that we have to take the square root of 0.56794. And so the estimated variance then of the point estimator, which gives us a point estimate of 19.22, the estimated variance of that quantity of that estimate is 0.56794. So we take the square root of that to get the standard error, the estimated standard error, multiply that by the t-value. All right, that gives us the margin of error. We subtract that from the point estimate, add it to the point estimate, and then we get our confidence interval. And so that confidence interval ranges from 17.66 up to 20.78. And so when x1 is equal to 8 and x2 is equal to 275, we are 95% confident that the average delivery time is somewhere between 17.66 minutes and 20.78 minutes. All right, and so then finally, this has some useful information on this slide, and this is taken from the textbook. The length of the confidence interval, or the mean response, whichever confidence interval if we're looking at the confidence interval for a beta parameter or for the mean response, it's a useful measure of the quality of the regression model, and we can use this to better understand the benefit of having more than one explanatory variable. And we can see this when we compare different models. And so to illustrate, consider the 95% confidence interval on the mean delivery time when x1 is equal to 8 cases, and x2 is equal to 275 feet. All right, and so we just saw this. And the width of that interval, which ranges from 17.66 minutes up to 20.78 minutes, the length of that interval is 3.12 minutes. Now, consider the simple linear regression model with that contains just x1. So x1 being the number of cases, and that's the only explanatory variable. The 95% confidence interval for the mean delivery time in that case ranged from 18.99 minutes up to 22.97 minutes. The length of that interval is 3.45 minutes. Now that's a wider interval. And so what we can see here is that incorporating an additional variable, the distance that the delivery driver has to walk, has provided more information to the model, and it allows us to come up with a more precise interval. You'll remember that narrower intervals are more precise, wider intervals are less precise. And so adding that extra, that additional variable allows us to come up with a more precise estimator for the average delivery time. Now, the other thing that this is pointing out is that if you do that kind of a comparison, comparing, say, the width of a confidence interval for a simple linear regression model, as was constructed in Chapter 2, with the width of a confidence interval when you've got, let's say, 2 explanatory variables. You could use more, but let's just focus on the 2 explanatory variables that we've got here, that the difference in the widths is going to depend on the values of the x variables that you're looking at. And what you would find is that the further you get from the centroid of the explanatory variables, the explanatory variable space, the greater that difference is. And so as you look at explanatory variables, or if you estimate the mean the response at values of the explanatory variables that are further and further away from that centroid of that explanatory variable space, then there's going to be a greater and greater benefit for having the additional variables. So that's what they're talking about here. All right, now it's also important to take into account how many confidence intervals that we're constructing. And for example, if we are constructing confidence intervals for the slope coefficients, then the more slope coefficients that we have, the more confidence intervals we're going to be constructing, assuming that we want to construct confidence intervals for, let's say, all of the slope coefficients. And you'll recall from your first methods class, and I'm sure it's been reiterated through all of your statistical methods classes, that the more comparisons you make, or the more confidence intervals that you construct, the greater the probability that at least one of those comparisons is going to lead to a type 1 error. Or in the context of confidence interval estimation, the more confidence intervals that you construct, the greater the probability that at least one of those confidence intervals does not contain the parameter it's estimating. And so it's important to maintain control over the probability of that happening. And one way to do that is to look at procedures for constructing simultaneous confidence intervals, or for constructing a confidence region for those parameters. And so one way to do that, and this is a very important way to do this, is to utilize the fact that this quantity here follows an F distribution with P numerator degrees of freedom and N minus P denominator degrees of freedom. And taking that into account, we can come up with this particular procedure that says that the joint confidence region for all the parameters in the parameter vector, that confidence region, all right, is given by the set of parameter points that satisfy this inequality. So all points in the parameter space for which this quadratic form, it's actually a ratio of variance estimators, but this ratio is less than or equal to the upper alpha percentage point of the F distribution, with P numerator degrees of freedom and N minus P denominator degrees of freedom. So all points in the parameter space that satisfy this inequality belong to a joint confidence region that has a coverage probability of 1 minus alpha times, well, 1 minus alpha would be the probability, and then the what we would call the confidence level would be 1 minus alpha times 100%. So this is very useful, at least if we've got a small number of well, this is useful regardless. But if we wanted to see what this looks like graphically, we can only really graph this if we've got 1 or 2 explanatory variables. If we've got 1 explanatory variable, then this the points on the boundary of this space, of this region, or an ellipse. And if we have 2 explanatory variables, then the boundary of this set would be an ellipsoid, so it would look like a football. Okay. Once we get beyond 2 explanatory variables, we really can't plot this, at least not for all of the dimensions that are there. But we can use this to query is a particular parameter point in that confidence region. Okay, so that is all the material in the notes for that section. I've written a few more notes to discuss another procedure. Another procedure for constructing simultaneous confidence intervals. They do talk about this a little bit in the text, but they did not provide any of this in their slides. So I created some slides for this. So let's look at this. How to construct simultaneous confidence intervals that are based on the Bonferroni inequality. And so let's first review the Bonferroni inequality. You probably saw this in your first methods class. And so let's let A1, A2, and so forth up to A sub k be a collection of events defined on the sample space of some random experiment. The union of those events is itself an event, and in particular, it's the event that at least one of the events, A1 through A sub k, occurs. All right? Now, the Bonferroni inequality states that the probability that at least one of the events occurs is less than or equal to the sum of the probabilities of each individual event occurring. That is, the probability that at least one of the events A1 through AK occurs is less than or equal to the sum of the individual probabilities of the events. So that is the Bonferroni inequality that gives us an upper bound on the probability that at least one of these events occurs. Now, let's apply this to this situation where we want to construct simultaneous confidence intervals. So suppose that k parameters are to be estimated using significant confidence intervals, and that each individual confidence interval possesses a confidence level of 1 minus alpha sub I times 100%. All right, so this I in the subscript, that's going to, that represents or stands for the individual confidence intervals. Okay, and so we have k parameters that we're wanting to estimate using confidence intervals. And let's suppose that we have a confidence interval for each of those k parameters, and each of those confidence intervals has a confidence level equal to this quantity. Now, given that, what can be known about the simultaneous confidence level for the entire set of k intervals? In other words, what is the probability that the k confidence intervals all contain the parameters that they are estimating? What is the probability that all of those confidence intervals cover their associated parameters? Well, we can answer that using the Bonferroni inequality. So for each I going from 1 up to k, let's define the following events. A sub I is defined to be the event that the confidence interval I contains the parameter it is estimating. So A1 is the event that confidence interval 1 contains its parameter. A2 is the event that confidence interval 2 contains the parameter it's estimating, and so forth up to K. Then with that notation, the intersection of those events is the event that all K confidence intervals contain the parameter that they are estimating. The complement of that, which is the union of the complements of these individual events, is the event that at least one of the confidence intervals does not contain the parameter it's estimating. Now, since each confidence interval has a confidence level equal to 1 minus alpha sub I times 100%, it follows that for each I going from 1 up to K, the probability of A sub I is equal to 1 minus alpha sub I. Okay, that's the probability that the ith interval contains the parameter it's estimating. And then by the complement rule, the probability of A sub I complement is equal to 1 minus the probability of A sub I. And that's equal to 1 minus that quantity. And so it turns out that the probability that the ith interval does not contain its parameter is alpha sub I. Okay. The probability that at least one of the confidence intervals does not contain the parameter it's estimating is given by the probability of the union of the A sub I complements. And from the Bonferroni inequality, we now know that that probability is less than or equal to the sum of these probabilities, these individual probabilities. Each of these is equal to alpha sub I. And so we're just adding up alpha sub I K times, and so that's just K times alpha sub I. Now, a lower bound for the probability that all confidence intervals contain the parameter they're estimating is therefore equal to 1 minus K times alpha sub I. So in other words, the probability that all of the intervals contain the parameter that they are estimating is equal to this quantity, all right, which is greater than or equal to, and again, this is because of the Bonferroni inequality, and then we're moving some things around algebraically, but this is greater than or equal to, it's at least 1 minus K times alpha sub I. Now, suppose we want this probability. Suppose we want the probability that all confidence intervals contain the parameter they are estimating to be at least 1 minus alpha sub s. So we can accomplish that if we set alpha sub I equal to alpha sub s over K. And by the way, this alpha sub s, this s here represents simultaneous, all right? And so if we set alpha sub I equal to alpha sub s over K, then the probability that all confidence intervals contain the parameter they're estimating will be at least 1 minus alpha sub s, which is what was required. Okay, and so this shows us how to construct these kind of simultaneous intervals using the Bonferroni approach, because it follows that so to construct a set of K confidence intervals possessing a simultaneous coverage probability of at least 1 minus alpha sub s times 100%, it suffices that each confidence interval have an individual confidence level equal to 1 minus alpha sub s over K times 100%. Now, note that this approach is conservative, since the probability that all confidence intervals contain the parameter they're estimating is greater than or equal to 1 minus alpha sub s. And so in that sense, this is conservative. So we may want this lower bound to be 95%. We may construct these confidence intervals in such a way that the simultaneous coverage probability is at least 95%, but it's very likely that the coverage probability will be actually greater than that, but it's not going to be less than that. And so that is that is how we go about doing it. So for example, suppose we have k equal to 5 confidence intervals that we want to construct, and we must have a simultaneous coverage probability of at least 95%. Then this can be accomplished by constructing the individual intervals, right? Constructing each interval having a confidence level of 99%. So if we fit these 5 confidence intervals, each with a confidence level of 99%, then jointly, those confidence intervals will have a simultaneous coverage probability or a simultaneous confidence level of 95%. If we have k equal to 10 confidence intervals that must have a simultaneous coverage probability of at least 95%, then this can be accomplished using this procedure by constructing the 10 individual confidence intervals, each with an individual confidence level of 99.5%. So that's how we can use this Bonferroni approach to very easily construct simultaneous confidence intervals. In other words, a set of confidence intervals that have a given or satisfy a given confidence level simultaneously. All right, so let's see how we can implement these techniques in SAS. And in particular, we'll start off looking at PROC IML. And so we're going to look at example 3.8. This is, again, the delivery time data set. And we're going to construct the 95% confidence interval estimate of beta 1, the slope coefficient on the number of cases to be delivered. All right, so you'll recall that we have this multiple regression model containing 2 explanatory variables. And we're going to construct the 95% confidence interval estimate of beta 1. Now, again, the general form of a confidence interval is given here. We start off with a point estimator, and then we go a distance to the left and to the right equal to the margin of error, where the margin of error is given by or equal to an interval coefficient times the estimated standard error of the point estimate. Now, in the context of multiple regression with normally distributed errors, the interval coefficient comes from students' t-distribution. And in particular, for a 2-sided 1 minus alpha times 100% confidence interval, the interval coefficient is the upper alpha over 2 percentage point of the t-distribution with degrees of freedom that are equal to the degrees of freedom associated with the MSE in the ANOVA table. And we know that that quantity, that number of degrees of freedom, is n minus p. Okay, so that's what we're going to be doing in this particular program, this PROC IML program. And so let's scroll down and take a look at how we do this. Now, the first thing I want to do in this particular example, what I'm going to do is show you how to read in a SAS data set, right? Instead of incorporating or creating the required vectors by inputting them as matrix literals, we're going to read the data set in it. And just in case, well, I think we've already seen this, but I'll show it to you just again. So we have to create a libref using the lib name statement. The libref in this case is SAS underscore data. And what this is essentially a pointer to the directory in which I've got the data set. Right. And so if you download this and use it, you'll have to change this to wherever it is on your computer that you've saved that data set. All right, so then we're going to create a temporary version of the data set. I'm going to call it EX08 for example 8. We open up the actual data set, all right, that populates the temporary data set. And then you'll recall that in PROC IML, we're going to need a column of 1s in the design matrix. And so what I'm going to do is I'm going to create a variable in the data step here. I'm going to call that variable 1s. And that variable is just going to contain a 1 for each observation. All right, then we invoke PROC IML. We use the temporary SAS data set that tells SAS to open it up. And then we're going to read the variables into the appropriate vectors or matrices. So we're going to read the variable delivery time into the y vector, and then we'll read in the variables ones, number of cases, and distance into the design matrix X. All right, and then I'm going to analyze. I'm going to fit the model. So let me just say that here. We're going to fit the model. I'm not talking about full models and reduced models here, so I'll just change that language there. So we're going to fit the model, and we've seen how to do it, so I'm not going to spend any time looking at that. So I'm just going to scroll on down to the very bottom, and it's down here where we're going to construct a 95% confidence interval estimate for beta 1. All right, and so we need the covariance matrix. All right, and let's see, I've created that up above. So here I'm calculating the estimated covariance matrix of beta hat. I'm going to call that b hat cov, and that's equal to the product of the mean squared error with the x prime x inverse matrix. And I'm just going to put that whole thing, the resulting matrix, in b hat cov. So now I can very easily get the variance that I need. All right, so I'm going to be consistent with how the book represents this, I'm going to call that C. Okay, in this particular section, we get our t-value using the t-inverse function in SAS. We calculate the standard error, the estimated standard error of beta 1 hat. That's equal to the square root of the second diagonal element in the estimated covariance matrix. Now, just let me point something out here, that in the notes in the book, they subscripted C with 1, 1, but the difference is they are starting their counting at 0, 0 corresponding to the intercept, and then 1 corresponding to beta 1, 2 corresponding to beta 2. All right, but it's a 3 by 3 matrix, and we have to, the way we address or access these entries in matrices in SAS, we can't start at 0. We have to start at 1. All right, and so that's the difference between what I've got here and what's in the book. Okay, then we construct the lower confidence limit by subtracting the product of the interval coefficient and the estimated standard error of beta 1 hat from beta 1 hat, which is contained in the second entry in b hat. That gives us the lower confidence limit. And then to get the upper confidence limit, we just add that product to the point estimator. All right, and so then when we do that, we're going to get those values. And so let's run this and check and see what we get here. All right, so here I have output from the fitting. We're not interested in that right now. What we want is down here at the very bottom, the 95% confidence interval estimate of beta 1, and we get a lower confidence limit of 1.2618247 and an upper confidence limit of 1.9699898. And if we round that to the number of decimal places given in the book, then we should get the exact same value. So that is how we can construct confidence intervals for the slope coefficients. What I'm doing here is just implementing that formula that we saw in the textbook, and really implementing that basic form that we saw even back in our first statistical methods class. Okay, now let's look at PROC REG and how to do this in PROC REG. What we're going to see is that it takes much less work to get this done in PROC REG than it does in PROC IML, which is expected, all right? And so here we're going to use PROC REG to obtain point and confidence interval estimates of the slope coefficients, all right? And so we're going to invoke PROC REG. And again, so I can focus on the appropriate part of the output, I'm going to suppress all plots, and I'm going to print out only the parameter estimates table. Now, in order to get the parameter estimates table to include the confidence limits, we need to issue the CLB, the confidence limits for the betas option after or as part of the model statement. So after we list the last explanatory variable, we have a forward slash, all right, indicating that we've got some options after that. And the only option we need to get this done is CLB. So again, this instructs SAS to calculate and provide the confidence limits for the betas. And so let's run this and see what we get. All right, so again, I'm just printing out the parameter estimates table. And so let me take a look here. So as we typically have the parameter estimates. So for example, the parameter estimate for beta 1, so beta 1 hat is 1.61591. All right, what we see here out to the right, these are the lower and upper endpoints for 95% confidence intervals for each of the beta parameters in the model. So we have these confidence limits not only for beta 1, which goes from 1.26182 up to 1.96999, but we also have the confidence limits for beta 2 hat, or I'm sorry, confidence limits for beta 2, right? So here's the point estimate for that beta 2 hat, 0.01438. We're 95% confident that beta 2 is somewhere between 0.00689 and 0.02188. We also have confidence limits for the intercept beta 0. The point estimate of beta 0 is beta 0 hat, which is equal to 2.34123. And the 95% confidence limits or confidence interval for beta 0 ranges from 0.06675 up to 4.61571. So we see here that with not a whole lot of work, all we have to do is issue the appropriate option to the model statement. We're going to get the confidence limits for the beta parameters. All right, now let's look at example 3.9. All right, and what we're wanting to do in this example is to construct a 95% confidence interval estimate of the mean delivery time, the mean value of y, when x1 is equal to 8 and x2 is equal to 275. Okay, now, again, we're going to start by looking at PROC IML. And so we have the same type of code that we had as we had in here for the previous example. All right, and again, let me just say we're going to fit the model. All right, and let's scroll down here to the very end. So you can see there's a little bit more to do here. All right, so we're going to construct a 95% confidence interval estimate for the expected value of y, given that x1 is equal to 8 and x2 is equal to 275. And we're going to do this two ways. We're first going to use an explicit expanded formula for the variance that can be obtained by expanding that quadratic form for the variance. And then we'll actually use that quadratic form written in matrix notation or in the matrix form of that variance below. But let's take a look and see how to do this with this expanded formula. So we're going to, we set the variable x1. We're going to create a variable in x1 and set it equal to 8. All right, we create a variable x2 and set it equal to 275. So once we've done that, then the estimated value, the point estimate for the expected value of y at that particular setting of the x variables is equal to beta 0 hat, which is obtained by that entry, that value. And then beta 1 hat times x1 plus beta 2 hat times x2. So that gives us our point estimate for the expected value of y, given that x1 is equal to 8, x2 is equal to 275. All right. Again, I need the covariance matrix for the beta hat vector. And then the expanded formula for the variance is expressed, it's implemented using this formula here. And so for practice purposes, go ahead and expand that quadratic form and make sure that you get an equivalent formula. So we're going to use that to calculate the variance, and then we take the square root of that to get the estimated standard error. We get our t-value, and then we construct the lower and upper confidence limits as usual. All right, and so then we will print out the x values at which we're wanting to estimate y. We'll print out the point estimate of y, and then we'll print out the lower and upper confidence limits. Okay, we can also do this using the matrix formula for the variance of y. No, I'm sorry, the variance of y hat. And so what we're going to do here, we need a vector containing the values of x1 and x2, as well as the 1, right, to pull off or to multiply against that intercept. And so I'm going to call that x vector x star. We've already got x, that's the design matrix, right? And so I'm just going to name this something else. So I'll call it x star, right, to contain those values. And then we are going to first calculate the estimated value of the expected value of y, given the x's, as the inner product of x star and beta hat. We then calculate the variance, the estimated variance of y hat, and that's given by this quadratic form. So the transpose of x star times the estimated covariance matrix, b hat cov, times x star itself. So that gives us the estimated variance of y hat. We calculate the square root of that to get the estimated standard error of y hat. We get the t-value, we construct the confidence limits as usual, and then we'll print those out. Okay, so that is what we're going to do. So let me go ahead and run that. Okay, and so we've got two sections we're going to look at. We're constructing the 95% confidence interval estimate for the expected value of y given the x's, x1 equal to 8, x2 equal to 275. And so the point estimate for the expected value of y at those values of x1 and x2 would be 19.2243. That's exactly what we got before. And then the lower and upper confidence limits are 17.6539 and 20.7947. Okay, and so if you look in the textbook, those should match up. Then we're using, in the second formulation, we're using the matrix formula for the variance of y hat. And so you see here, when we do that, we get the same exact lower and upper confidence limits that we had using the expanded formula for the variance. All right, so that's how we can estimate the average value of the response at given values of the explanatory variables with PROC IML. Now, let's move to PROC REG and see how to do that same thing. All right, so again, this is still example 3.9. Construct the 95% confidence interval estimate of y when x1 is equal to 8 and x2 is equal to 275. Now, in this case, I'm going to, just to make this easier to show, I'm going to enter the data into a data, using a data step, and enter that into a data set called delivery time, where I've got the raw data here, right? So I just pasted it from a spreadsheet. At the very end, okay, I'm going to include a line that has x1 equal to 8, x2 equal to 275, right? Which is the points, or the point at which we're wanting to estimate the expected value of y. But we're going to leave the value of y, the value of delivery time, we're going to leave that missing. And the way we do that is by entering a dot. Okay, you don't leave a space if you leave it blank, if you have a space there, it's not going to read this correctly, right? The dot is what SAS uses to represent a missing value. Now, by including this line, and in particular by including the dot there so that the response is missing, SAS is not going to use that line in that line of data in fitting the model. And so the default in SAS in virtually all procedures, and you really can't get around this in most procedures, and you wouldn't want to, but if there's missing values in any of the variables in a given observation, then in fitting models and doing things like this, SAS is going to exclude that observation from the fitting process. But it will include this when it goes to computing predicted values, constructing confidence limits, and so forth. And so that's why we use this. Okay, so let's see how to do this. We're using PROC REG to obtain point and confidence interval estimates. Actually, I say here of the slope coefficients, but no, it's we're estimating the average value of y given x. I'll correct that. Now, how do we do this? Well, we have to do a couple things. Number one, we have to issue the CLM option after the model statement. Then we have to create an output data set, and we have to, I'm going to output the predicted values or the estimated values of the expected value of y. And then we have to output the lower confidence limits for the mean and the upper confidence limits for the mean to that output data set. The name of that output data set in this example is out1. And so then once we have that, we're going to print out the contents of out1. All right, and so, one thing, look at the, I want you to see this. What I'm going to do is I'm going to only select or only print out the rows in that data set where x1 is equal to 8 and x2 is equal to 275. All right, and so we don't have to look through, we don't have to scan through all of the output to find the values we want. We'll just, it'll print out just what we're wanting. Okay, so let's run this. Okay, and we see here that we have the estimate of y, the estimate of the expected value of y when x1 is equal to 8 and x2 is equal to 275. That point estimate is 19.2243. And then we have lower and upper confidence limits for that expected value of 17.6539 and 20.7947. So that's exactly what we got using the procedure that we implemented in PROC IML. But the good thing is, the nice thing is that we don't have to, if we're using PROC REG and we use this capability, we don't have to validate anything. We don't have to quality check it, right? That's already been done by the folks at SAS. All right, finally, let's look at example 3.10. Now, this deals with the rocket propellant data. In this example, we will construct 3 pairs of simultaneous confidence intervals for beta 0 and beta 1. The 3 pairs of simultaneous two-sided confidence intervals will be constructed at the 90%, 95%, and 99% levels of confidence, respectively. So in this example that we're doing here, we're going to do a little bit more than what they're doing in the book. In the book, in this example, they construct simultaneous 90% confidence intervals, but we're going to go ahead and add 95% and 99% intervals as well. Now, the Bonferroni approach will be used in constructing these simultaneous confidence intervals. Using this approach, to construct simultaneous two-sided confidence intervals for k parameters with a joint or simultaneous 1 minus alpha times 100% level of confidence, each of the individual confidence intervals must be constructed at the confidence level equal to 1 minus alpha over k times 100%, just as we saw in the notes that we went over. Now, in this example, k is equal to 2, and so each of the individual confidence intervals must have a 1 minus alpha over 2 times 100% confidence level. Now, for the joint confidence levels that we'll be using in this example, the table below contains the individual confidence levels at which each confidence interval must be constructed. So here we have this table containing 4 columns. The first column contains the desired simultaneous confidence level that we want. We're going to do 3, 90%, 95%, 99%. And then again, confidence levels are expressed as 1 minus some alpha times 100%. And so when the confidence, with a simultaneous confidence level of 90%, the corresponding alpha is 0.1, 90% divided by, or 1 minus the 90% divided by 100%. All right, so that alpha is 0.1. And then because we're going to be constructing 2 simultaneous confidence intervals using the Bonferroni approach, we have to divide that alpha by 2, and that will give us then the individual confidence intervals to use for each of the 2 confidence intervals that we construct. And so if alpha is equal to 0.1, obviously alpha over 2 is 0.05. And so the individual confidence level that will give us, well, let me put it this way, the individual confidence level for each of the 2 confidence intervals must be 95%. And if we do that, then we will have simultaneous confidence intervals with a simultaneous confidence level of 90%. To have a simultaneous confidence level of 95%, the alpha associated with that confidence level is 0.05. We divide that by 2, 0.025. And so if we construct the 2 intervals at the 97.5% individual confidence level, that will give us simultaneous confidence level of 95%. And then finally, if we want a 99% simultaneous confidence level, the alpha corresponding to that confidence level is 0.01. We divide that by 2, we get 0.005. And the corresponding individual confidence level for each of the 2 intervals is therefore 99.5%. So if we construct each of those 2 confidence intervals at the 99.5%, then jointly they will have a 99% simultaneous confidence level. So that's the approach that we're going to use. And we need to know the values in this column here, the alpha over 2 column, because these are the values that we're going to supply to PROC REG to tell it how to construct the intervals. The default is for PROC REG to construct individual 95% confidence intervals. All right, but we can adjust that by specifying different values, and it will construct the appropriate intervals. Okay, so what I'm going to do first is I'm going to create a data set. I'll call it T values. And this data set will contain the interval coefficients for 90%, 95%, and 99% simultaneous confidence levels. And so the degrees of freedom for error for this example is 18. And then I've got a little do loop here. All right. And so for my simultaneous confidence levels, which I'm denoting by CL_S, of 90%, 95%, and 99%, I'm going to do these steps. And so I'm first going to identify the alpha value associated with each of those confidence levels. I'll then, and these are the simultaneous alphas, I'll then from that calculate the individual alphas. All right, so just dividing the simultaneous alpha by 2. So I'm calculating these values in this step. And then once I have that, I will calculate the individual interval confidence levels, giving me the values in this column. And then once I have the individual alpha level, I'm going to supply that to the T inverse function. All right, and so I need the upper, the t value corresponding to the upper tail. And so I subtract the alpha underscore I over 2 from 1. And then I have to, as the second argument, supply the degrees of freedom. And so that I calculate the t value, the interval coefficient. And then we'll print those values out. So let me go ahead and run all of this. And so we'll first get this table of t values. And so for two simultaneous confidence intervals at the 90%, at the simultaneous 90% confidence level, the corresponding t value is 2.10092. The t value for two simultaneous confidence intervals at the 95% simultaneous confidence level, that would be 2.44501. And in order to have a simultaneous confidence level of 99% for two intervals, the corresponding t value would be 3.19657. All right, so now let's look down here at the SAS code. And I'm going to invoke PROC REG 3 times, one for each of the confidence levels that we want. We want simultaneous 90% confidence interval estimates, 95% simultaneous confidence interval estimates, and then finally simultaneous 99% confidence interval estimates. And what we need to do is to indicate to PROC REG the level of confidence that we want to construct these individual confidence intervals at. We use the alpha option on the PROC REG statement itself. All right, and so for the first interval, the first set of intervals, in order to construct 90% simultaneous confidence intervals, the value we specify and feed to the alpha statement, or the alpha option, is 0.05. All right, and so that's what we're going to do here. To construct the 95% simultaneous confidence intervals, we specify 0.025 to the alpha option. And then to construct the 99% simultaneous confidence intervals, we specify 0.005 as indicated up here. In the output to SAS, for each of these, it's going to report that the confidence levels are as reported in this last column. Okay, so let's go ahead and run this. We'll run these statements. Okay, so here is the information for the simultaneous 90% confidence interval estimates of beta 0 and beta 1. In the parameter estimates table, all right, we have the last two columns giving us the lower and upper endpoints of, in this case, individual 95% confidence intervals. All right, and so for example, the lower endpoint for the confidence interval for beta 0, 2534.9954. The upper endpoint, 2720.6493. And then for beta 1, the lower confidence limit is negative 43.2234 approximately. And then the upper endpoint would be negative 31.0838. So individually, these are 95% confidence intervals. This is so what we would say here, to interpret it that way, we could say that we are 95% confident that beta 0 is somewhere between 2534.9954 and 2720.6493. Likewise, we would say that we are 95% confident that beta 1 is somewhere between negative 43.2234 and negative 31.0838. But we could also say that we are 90% confident that beta 0 is between, again, these two values, and beta 1 is between those two values. So that 90% applies to both intervals simultaneously. All right, for the simultaneous 95% confidence interval estimates of beta 0 and beta 1, we would need to construct individual 97.5% confidence intervals. And so individually, we would say that we're 97.5% confident that beta 0 is somewhere between 2519.79245 and 27.35.85227. Similarly, we are 97.5% confident that beta 1 is somewhere between negative 44.21747 and negative 30.808971. But jointly, we are 95% confident that beta 0 is between those two values and beta 1 is between these two values. And then finally, we have the same kind of result to construct 99% simultaneous confidence intervals. We would need to construct individual intervals, each at the 99.5% confidence level. And so we would say that individually, all right, we are 99.5% confident that beta 0 is between 2486.5852 and 2769.0595. Similarly, we're 99.5% confident that beta 1 is between negative 46.3888 and negative 27.9184. But jointly, we are 99% confident that beta 0 is between those values and beta 1 is between those values. So that's how we can construct joint or simultaneous confidence intervals where the confidence level applies to the entire set of confidence intervals that we're constructing. And if we had more parameters, maybe we have a multiple regression model where we have not only the slope coefficient, but we've also got two slope coefficients. And so in that case, instead of dividing by 2, we would divide alpha by 3. And we would have a column here in this table, alpha over 3. Those are the values that we would specify to the alpha option in PROC REG. So that's how you can do it very easily. And again, it doesn't take any fancy programming. All it takes is a little bit of thought and understanding how this works. Now, again, these, as we indicated when we went through those notes, these specified simultaneous confidence levels are conservative. The coverage probability of 90% is a lower bound. And so the actual coverage probability could be, and probably is, greater than that. All right. And so in that case, it's conservative. Likewise, these intervals, these intervals have a simultaneous confidence level of at least 95%. And these intervals have a simultaneous confidence level of at least 99%. And the other thing to notice, and you know this very well, that as you increase the confidence level, the width of the intervals increases. All right, so these are the narrowest intervals in this set, and these are the widest intervals in this set.